Today I'm here to tell the presentation of the NP. What is meaning of the NP? NP is an abbreviation of non-polynomials. NP hard, NP complete. There are many types of concepts we are using here. And we are using some real life examples like Sudoku. Like Sudoku, 8 pins problem, we are using that. And we are using some backtracking techniques for solving these techniques. And let's begin with the slides. First, we are telling about the NP. NP is the non-deterministic polynomials. Next, NP complete, NP hard. We are telling all these topics using the NP hard problems. So we are mainly targeting NP means traveling salesman problem. What is traveling salesman problem? Mainly tells you about how the traveling salesman person should take a less distance, but he has to cover more places. That's the traveling salesman problem. We have done many methods for the traveling salesman problem, like graph method, branch and bound method. There are many methods for solving the traveling salesman problem, and we are using by traveling salesman problem we will get the NP complete methods very easily. There are some methods for using NP complete, NP hard problem. All compared to these NP complete, NP hard. NP hard is considered as the most difficult part of the life, and traveling salesman problem is considered as the most important topic of the syllabus of the DAA. DAA is the abbreviation of design of analysis and algorithms.
Chaudhary from section Z, let us explore the slide 3, which talks about NP hard problems, one of the most important concepts in computational complexity theory. First, what does NP hard means? An NP hard problem is a problem that is at least as difficult as the hardest problem in NP. That means if we somehow find a fast solution to any one NP hard problem, then every problem in NP can also solve fast. So these problems sit at the top level of the difficulty in the computer science. One most point in that NP problems do not have to be the NP. For NP problems we can verify a solution quickly, but NP hard problems may not even be verifiable. Some do not have a clear yes or no answer or might not be computable at all. That's why NP hard presents as a much border classes. To understand better, let me give an example for the slide that halting problems. The halting problems ask given a computer program and an input which the program eventually stops or will the run forever. At first it sounds simply, but it actually impossible to design an algorithm that answers this correctly for every possible program. What is the NP hard? Because we cannot solve it algorithmically, we cannot even verify most cases efficiently, and solving it would magically allows us to solve even problems in NP and NP complete. This shows how NP hard problems can be extremely complex, sometimes beyond the limits of computation. So that the summarize of the slide 3 is NP hard problems are the hardest classes of the problems known. They may not be verifiable in polynomial times. Solving one fast meaning we can solve all NP problems fast, and the halting problems is a classical example. Now let's go to the slide 4. Now coming to slide 4, which lists some examples of NP problems. Before we discuss the examples, remember the key idea of NP problems. A problem is a NP if you give a solution we can verify it quickly, even if finding the solution may be very difficult. Let's go through the examples on the slide. Sudoku puzzle. Solve it from the scratch might take a long time, but once you can see complete grid, checking it is correctly in extremely quick. So Sudoku belongs to NP. Hamiltonian cycle problem. This question is, does a graph contain a cycle that visits every vertex exactly once? Verify given cycle is easy, just check the order of the vertices. Subset sum problems. Given a list of numbers, in there are subset whose sum are equal and target values. Hard to find but easy to verify once you show the subsets. TSC, decision variable. Instead of finding the shortest path, the decision version task in their route shortest than their given distance. Check a particular route in example. Graph coloring problems. Can we color a graph using only k color without any two adjacent nodes sharing the same color? If someone gives a coloring, check it easily. Boolean satisfiable SAT. This asks whether a logical expression can be made true by some combinations of variable assignments. The answer only once give a true assignment we can quickly verify it. Knapsack decision problem. Uh, Giving an weight limit, can we choose items that fit with a limit and reach at the least a target value? Answer again, verifying a possible set of items in simple. Job scheduling problem. Checking the completion time of the given schedule is easy, even though finding the best schedule is extremely hard. All those problems share one thing: solving them may take exponential time, but verifying a provided solution take polynomial time. That's why they belongs to NP. Uh, List of real world and theoretical problems that are difficult to solve but easy to verify. Thank you.
Now let's look at one of the most important categories in computational theory, NP-complete problems. To understand NP-complete, think of it as a special corner inside NP that contains the hardest problems of the group. A problem is called NP-complete only if two major conditions are satisfied. Condition 1, if it belongs to NP. Condition 2, if it belongs to NP-hard. What so we will look into what is NP. This means that once someone gives you a solution, you can verify it quickly. You may take some time to find the answer, but checking it is easy. Condition 2, it is NP hard. This means it is difficult as the hardest problems in NP, and every problem in NP can be reduced or converted to this one in polynomial time. So when we get these two conditions together, we get NP complete problems are the toughest problems inside NP. Why are they important? Because solving even one NP complete problem in polynomial time would mean all problems in NP can be solved quickly. Computer science would change forever. We should answer the biggest open question: P versus NP. Let me make it very clear with an example shown in the slide. Travel screen, travel salesman's problem, TSP. In TSP, a salesman must visit each city exactly once and return to the starting point using the shortest possible route. Why is this NP complete? Checking whether a given path is valid and computing its length is fast. So it's belong to NP. But finding the best possible route among all combinations is extremely difficult. Making it NP hard. So since it satisfies both conditions, it becomes NP complete. There are many other famous NP complete problems too, like three set, subset, and graph coloring. What makes an NP complete problem interesting is that they sit at the edge of what is solvable efficiently. They challenge us to design smarter algorithms. They help define limits of computation. So, whenever you hear NP is complete, think of it as problems that are easy to verify, hard to solve, and solving one efficiently would solve them all. That is, NP complete problems are the central focus in computational theory. So, coming to the next slide, we NP hard problems, which are even more challenging. NP hard stands for non demonstrative polynomial time hard. These problems are that are the least as hard as the hardest NP problems, but they have an additional twist. They do not have to be inside the NP, meaning we may not even able to verify solutions quickly. So NP hard is one of a higher level in difficulty. To understand NP hard better, let's compare it with NP complete. NP complete problems are inside NP. We can verify their solutions. And NP hard problems may or may not be in the NP. We may not be able to verify their solutions efficiently. That means every NP complete problem is NP hard, but not every NP hard problem is NP complete. One example from the slide is the halting problem. It asks, given a program and an input, will it stop or keep running forever? This sounds like a simple question, but we cannot design an algorithm that answers it correctly for all programs. Worse, we cannot even verify answers efficiently in most cases. So this makes the halting problem. NP hard, but not NP complete. Another important observation is that many real world life optimization problems like scheduling jobs across machines or assigning tasks efficiently also fall under NP hard, because as the number of tasks grows, the number of possible schedules grows explosively. So why do we study NP hard problems? Because they represent the limit of computational feasibility. If we solve hard problems efficiently, we can solve NP complete and NP problem efficiently too. They push researchers to develop heuristics, approximations, algorithms, and AI-based solutions. In real life, instead of perfect answers, we use greedy algorithms, genetic algorithms, priority heuristics, because exact computation becomes nearly impossible. So, summarizing, NP-hard problems are the most difficult class where finding the perfect answer is nearly impossible, and sometimes even verifying that answer is not feasible. This helps computer scientists judge which problems need exact solutions, which problem requires smart approximations, and where computing power reaches its limits. Thank you.
I'm going to tell you about the NP problems. There are some certain examples of NP problems such as Sudoku problem. Filling the 9 into 9 grid or 3 into 3 grid. Why NP? NP. We all know that Sudoku problem hard to solve but easy to verify. That's why we are using NP as the Sudoku problem. Hamilton cycle problem. Finding a cycle whether the graph visits in the vertex exactly once or twice, thrice or not. And why Hamilton cycle problem is considered as NP? You can verify by giving a cycle easily, but finding it very difficult. Subset sum problem. Suppose if you take in a set and take a numbers in that set, if you have a set, you have to add an element in the subset, and we are why NP is used, because subset is very fast and easy to find. Next, traveling salesman problem. Traveling salesman problem is mostly for the shortest path from one place to another place. The shortest path we are taking is known as traveling salesman problem. This is also an why traveling problem is considered as the NP, because it takes one route and possible others are extremely hard. Next, graph coloring problem. Coloring the graph by using K colors, and that's why it is also considered as NP. Next, Boolean satisfiability problem. Anyway, there are what is meant by Boolean. Boolean means true or false values. Assigning the true or false values to become a Boolean, and this is also considered as NP because taking one condition as easy. Next, knapsack decision. There are two types of knapsack: 0, 1 knapsack, fractional knapsack. By using those knapsack problems, we can find the value, and for the less amount of money, we are taking the more profit. That is called knapsack. Next, job scheduling problem. Initially, job scheduling problem is very easy, but when the people are increasing in the job, then only it becomes very difficult. Now in this slide, I'm going to tell you about the differences between NP complete and NP hard. Now let's go with NP hard, where we compare three very important classes in the computational complexity: NP, NP complete, NP hard. Understanding these differences is crucial because they help us classify how difficult a computational problem really is. Let's start with the NP. NP stands for the non-demonstratic polynomial time. A problem belongs to NP if when someone gives you a solution, you can whether it's correct quickly in a polynomial time. You know that polynomials, highest degree is known as the polynomials. This does not necessarily mean you find the solution quickly, but once the solution given, checking it is easy. For example, consider in a Sudoku puzzle. All of you know that about the Sudoku puzzle. Solving Sudoku can take a very long time, especially in the harder ones. But if someone shows you a complete grid, you can check it just in a few minutes. Because the person who is solving the Sudoku is very easy. But the person who is gonna check the whether it is correct or not is very difficult. Few seconds if each row, column and boxes is valid, whether the Sudoku is valid or not. That's why Sudoku fits in NP. Hard to solve, very easy to verify. What is the NP tells you about is the Sudoku is a hard to solve but easy to verify. That is why NP it is considered as the NP problem. Now let's talk about the NP complete problem. These are the hardest problem compared to the NP classes. Compared to the NP classes. For example, be an NP class, it must satisfy two conditions. But NP you can satisfy only one condition. Two conditions it must be NP, meaning we can check the correctness of the solution quickly. It must be NP hard, meaning every problem in the NP can be reduced it quickly. The example we are taking in the NP complete is about traveling salesman problem. If- Mostly the traveling salesman problem tells you about the how the work of the traveling salesman will be working. Like suppose there are six people in a traveling salesman problem. 6% should A is the first person and F is the last person. You have to go from A to F. Then we are taking the distance from A to F is considered as 150 kilometer. But from if you are going in a shortcut way, it gets 130 kilometers. Shortcut taking a shortest path is also known as the traveling salesman problem. If someone gives a proposed route, it can easily calculate the total distance by whether it verifies the requirement. But finding the shortest route requires checking an enormous number of possibilities, which makes the problem extremely difficult. That's why we are using the NP complete. Finally, we have NP hard problem. These are at least as difficult as the NP complete problems. These are also having the two-step verification, like a two-step method completion of the NP hard problems. These are these are at least as difficult as NP hard problems. However, NP hard problems do not to be in NP, which means we might not always be able to verify solution quickly. Some may not have any verifiable solution at all. A great example is the halting problem. Determining the program will eventually stop or run forever. There is no general algorithm to answer this, which makes NP hard. To summarize about all these things, about the difference between NP complete and NP hard. NP easy to verify solutions, but may hard to solve. NP complete hardest problems inside NP hard. NP complete at least as hard as NP is complete but may not have any variable solution. These distinction help researchers understand which problems efficient solution and which do not guiding algorithm designs and optimization. Now considering the real life application using the job scheduling problem. Let's look at the real life example of NP hard problem, the job scheduling problem. The problem is extremely important in industries like manufacturing, cloud computing, operating systems, and project management. The job scheduling problem is all about arranging a given set of jobs across one or more machines while optimizing some performance criteria. Think of like this. Suppose you run a manufacturing unit where multiple machines process different tasks. Each job may take different amounts of time on different machines or may specific guidelines or may depend on order in which other jobs are needed. Your goal might be minimized. If the total time to finish all jobs makes spanning trees, the waiting time, the idle time of the missions, or to finish the priority jobs earlier. These sound simple at first, but the complexity increases drastically as you add more jobs and as you more jobs are missions. What I'm telling you about the job scheduling problem is initially the condition will be easy, but when you are adding the people in the manufacturing company, it becomes difficult. This, for example, imagine you have three jobs and two missions. Each job takes a different time on mission. What would be the optimal way of the place? These jobs are total completion time is minimized. If you are checking every possible sequence manually, we could still manage it. But if we had 10 jobs, then we had 10 factorial. We all know that ten jobs means 10 factorial. 10 factorial means 10 jobs means we can arrange the 10 jobs into 10 factorial ways. 10 factorial arrangement. That means more than 3 million contributions, combinations. For 20 jobs, it becomes more than 2.4 quintillion possibilities. Impossible for any computer to test exhaustibility. That exactly why job scheduling classified as an NP hard problem. The number of possibility grows exponentially with each additional job, making the task exponentially infeasible to solve optimally in a reasonable time. Because of this real world systems often use heuristics or optimization algorithms like we all know that what is an algorithm. Algorithm is a step by step process of executing a task. There are many methods of doing this: greedy methods, priority based scheduling, genetic algorithms, robin scheduling, shortest shortest job first. These methods does not don't always give the perfect answer, but they provide a giving a quick answer.
Hello everyone. Today I am saying about job scheduling with deadlines. Example, there are 5 jobs are given. Let n equal to 5 jobs as J1, J2, J3, J4 and J5. These are the 5 tasks are given. If the task is completed within the timeline, they will get a profit. Profit as 20, 15, 10, 5, 1. But the job should be finished within the deadline. The deadlines are 2, 2, 1, 3, 3 for J1, J2, J3, J4, J5. Now let us assume there is a mission which could in which each job has to be proceeded. Let here deadlines as take has hours and profit as in rupees. Each job takes 1 unit of time. We are going to the next part. Example, make for example, we're taking a legal making documentation shop. There is a typist. You could complete each job in 1 hour. To understand the problem, we have to take that you open the shop in the morning. The people are waiting outside the shop. For example, the five jobs, and the third person, J3 person, he says that he should complete his job within the 1 hour of time. But whereas J4 job person saying that he could wait until 3 hours. Let us assume that if the shop opens at 9 a.m. in the morning, he could wait until 12 o'clock. But what are the profits we are getting? Assume profit in rupees. So which job should be done first? Highest profit should be done first. Now the problem is we want to set of those jobs can be complete within the deadline such that the profit is maximized. So this is an maximization problem or optimization problem. How many slots is having? From 0 to 1. He could complete one job. From 1 to 2, he could complete two jobs. From 2 to 3, he could complete three jobs. Only three slots are left. Here, no one is waiting beyond the time of 3 hours. He has to be finished within the 3 hours of time. For let us assume from 0 to 1 one job, and 1 to 2 second job, and 2 to 3 and third job. Let us take this time as 9, 10, 11, 12. Here there are three slots. He could finish within the deadlines. Out of 5 job J5, he could select only 3. So the problem is maximum. So the profit is maximum. From 0 to 1, the J2 from 0 to 1, 1 to 2. First we are taking J1 job. Here J1 job which has profit of 20 rupees, which could be placed in between 1 and 2, because you can wait until 2 hours. So from in between 1 to 2 we are placing J1, and from 0 to 1 we are placing J2, and we are not placing J3 because he could wait until only 1 o'clock. The profit is very low, so we are removing the J3. And from 2 to 3 we are placing J4 job, and J5 we are removing because it was least profit. Now we can see the available slots, and then we can place. So from 0 to 1, J2 job is placed. From 1 to 2, J1 job is placed. From 2 to 3, J4 job is placed. And now we are going to add this J2, J1, J4. 20 plus 15 plus 5, we are getting 40 as a profit. So in this is the possible way how we can get maximum profit by using this method, job scheduling with deadline. This is the easiest way in this maximization process. So we get 40 units as profit. Thank you.